Here are some notes on the symmetric difference quotient. This is in section 3.2, and we went over this in class, but it was kind of fast, so I just want to kind of elaborate on it a little bit. And what we have is, remember our two basic definitions for the derivative. This is the derivative of a function of x, f prime of x equals this limit, as h approaches 0 of f of x plus h minus f of x all over h. And then this is for the derivative at a point, and this is the alternate form. You can always derive the derivative, then we can let x equal a, and then we have a general form. So this is the f prime of a equals the limit as x approaches a of f of x minus f of a all over x minus a. In each case, you notice that the bottom goes to 0. And this is this basically is just our slope formula again. Now we're going to talk about the symmetric difference quotient. And what this is got here is and I drew a sketch over here and elaborated a little bit more. This is kind of like the sketch in the book. In other words, this is our function f of x, this curve here. And then this is the secant line, and this is the tangent line using these points. So rather than approaching from just one side, in other words, our original function was, or our original definition, we just approached from one side, and we're looking at this tangent, the secant line, which goes from here to here. And then as we get closer and closer, that line approaches the tangent line. And I don't have any of my little sticks here. I was looking for some of my little sticks. So you can see this, but I guess I could do it like this. This is the secant line, CB going between those 2 points. I think you can see it right over here. And as it's as h approaches 0, a plus h approaches a, and we get closer and closer and closer to the tangent line. And now the symmetric difference, it's a little more complicated when you're trying to evaluate derivatives using this definition, because we have to put a plus h and a minus h in our function. It becomes more complicated. So the definition down here is a little bit easier. Imagine if we had to do, f of x plus h minus f of x minus h. Then that would be a little bit different. It would be a lot more work. So this is a little bit more work, but it works better to get you a nice calculation. And this is what our calculators use. Because in other words, as h approaches 0, a plus h and a minus h both squeeze in. They both squeeze in to a, and the secant line is approaching the tangent line from 2 directions. So it starts over here like this, and then as h approaches 0, it gets closer and closer and closer until all of a sudden we're there. And that's the tangent line. So this is the symmetric difference quotient. Now remember, these are all basically difference quotients. The bottom is a difference. It's just simplified. Remember, it's just a plus h minus a, which ends up being h. And then this is a difference. So this is a difference quotient. This is a difference quotient. And this is what we call the symmetric difference quotient, because it's approaching from both sides, symmetrical to the around a. And remember, if this is a plus h, this point is a plus h, f of a plus h. If this is a minus h, this point is a minus h, f of a minus h. And if we just take the slope, which is just the average rate of change of the secant line, we get y2 minus y1 all over x2 minus x1, where we get this. So this is the same thing as our slope. And this is our average rate of change. But if we take the limit as delta x approaches 0, which in this case h would be approaching 0, then we're going to end up with just the tangent line. It's the same idea. It's just a third way of writing it. And we had diagrams for these other, we had sketches for these other 2 situations. So if we have a plus h times a minus h, if we remove the parentheses, we've got a plus h minus a plus h, because the negative times the negative is positive. So a minus a is 0, so we just have h plus h is 2h, so that's how this reduces. So it doesn't look like a difference on the bottom, but it actually, in its original form, is a difference. So that's what we call the symmetric difference quotient. Now, this works out so well that we don't really need to have super, super small values of h for it to work. So our calculators use h equal 0.001. So if we look up our calculators, we use NDERIV, that means the numerical derivative. Then our calculator works it out like this. It has all this kind of programmed in where it can actually find the derivative of a function at a point, as long as it exists. So this is going to be f of a, f prime of a. So this is the n derivative of f of a equals this, which actually would be just f prime of a. Okay, so this is the numerical derivative of f of a. And again, we just use 0.001 for h, and then 2 times 0.001 is 0.002. That's my cat, Soxy. He's having things to say. Okay. Anyway, so just ignore him. So we can see here that we have 0.002 is 2 times h. So this is basically what our calculator is going to be doing. Okay, so let's take a look at an example. Got one of those right here. So computing a numerical derivative, compute the NDERIV, or the numerical derivative of x cubed. And this is going to be x cubed with respect to x at x equals 2. So this is the notation. Some of your calculators work this a little bit differently, so I'll try to show you. Unfortunately, I don't have one of those, so I can't demonstrate with that, but I'll show you this. All right. So numerical derivative, x cubed, with respect to x at x equals 2. I'm going to use h equals 0.001. All right. All right, so this is what we've got. So we can write it over here. And then we're going to use just like we did over here, a plus 0.001 minus f of a minus 0.001, and that's going to be 0.00 over 0.002. So our point is going to be 2, so we just put 2 in. So 2 plus 0.001, that's f of 2 plus 0.001, minus f of 2 minus 0.001, all over 0.002. Now, my function is x cubed, so we're going to cube this. So that's what the rule is, cube whatever's in here. So we're going to cube, if we add these, it's just going to be 2.001 cubed. And then 2 minus 0.001 is just 1.999. So we're going to cube both of those because that's what the f rule says. The f function rule says that. And then we cube this, and you just put in your calculator. And that's the thing about these is you really have to use your calculator to kind of calculate some of these out anyway. So we would put 2.001, and we just math 3. And that's going to cube it, and we press enter, and this is the number we get. Now we're going to use this later, so we're going to store this. So I try to tell you and show you in class how to do this. So we're going to use the store button down here. So we'll just press store, and that's going to store this. I have to move this up a little bit so you can see all these things here. There we go. So I press store, and then I'm going to store this. And then we're going to use a letter, so we'll store this in alpha A, and that's going to put that in A. You can see that. And I press enter, and every time I press alpha A, I got that. Now the other one, if you look at your notes, was 1.999, and we'll math through that. And we get this 7.988000599, and I want to store that, one more line, excuse me, and we'll store that. So hit store down here, see this little store button, right above the on key is the store button, store, and then we'll go alpha, B is right over here, enter, and now we've got that stored at alpha B. So every time I put alpha A, I'm going to get the 8.01, etc. Every time I push the alpha B, I'm going to get 7.9, etc. So when we calculate this out, this is what we got here. When we calculate this out, this is what we got here. All over 0.002. Now, I wanted to see the difference, so rather than put those both in, I can just write it as alpha A minus alpha B, right over here. So we'll go alpha A minus alpha B, enter, And that's how we get the difference, which is the numerator of that fraction, 0.024 with all the zeros and 2. And then we want to divide that by, so we'll just put divided by 0.002, enter, and that's how we get the numerical derivative. Okay, so that's what we've got so far. And again, this is just what we did here. Store that in alpha A, hit that, get that, store that in alpha B. A minus B is that, then divide by 0.002, you get this. Now on our calculator, we can do that just by using Math 8. And that's kind of the easy way out. So let's clear all this stuff over here. And let's hit Math, over here, 8, Math 8. And that's going to give me a numerical derivative. Now my function is going to be x cubed, so I'll just put x, Math 3 there, comma, x, and comma. The comma's right over this number 7, but. And we're going to evaluate that at 2. So this is the numerical derivative of x cubed with respect to x at x equals 2. I put parentheses, and I press enter, and then we get the same thing. See, the calculator does all that work we did. It does all that. It's programmed in to do all that work. And that's how it figures out the numerical derivative. And you'll only have to do this twice on a couple of homework problems, and then after that we'll just use the calculator if we need numerical derivatives, because it does all that for us. Hope that all makes sense.